Once again, we discuss the properties of nuclear force. At the starting of this unit, we have already mentioned some properties, but now based on the studies or based on the observations that we have already made, the work that we have already done, we will discuss them again. And these are some main properties we got based on the discussions made so far. The nuclear forces are the strongest interaction in nature. The nuclear forces have a repulsive core. Nuclear forces have very short range of the order of 2 femtometer, not or of the order of 2 femtometer. The interaction between two nucleons consists to lowest order of an attractive central potential. The nucleon-nucleon force is charge symmetric. The nucleon-nucleon force is charge independent. We will explain these two terms. The nuclear forces are spin dependent. The internuclear potential includes a non-central term known as the tensor potential. The nucleon-nucleon interaction depends on the relative velocity or momentum of the nucleons. And we will give some explanations for this, and mainly for the last five. The first one says that the nuclear forces are the strongest interaction in nature. And this you can understand by this concept. The binding energy of neutron is 2.23 MeV, whereas the binding energy of the simplest atom, the hydrogen, which is due to electromagnetic force, is only 13.6 electron volt. So, its binding energy is a measure of the interaction. So, this is much stronger than, or you can see that this is nearly 10 raised to 6 times stronger than this. And nuclear forces have a repulsive core. Nucleons attract each other at a range of the order of 10 to the power of minus 15 meter or 1 Fermi. But the nature turns repulsive at substantially shorter distances. To explain this property, it is suggested that nuclear forces have a repulsive core. It means that at a very short distance, or they have a core which is known as up to the in that core you have the repulsive character. This conclusion follows from qualitative considerations of the nuclear density. As we add more nucleons, the nucleus grows in such a way that its central density remains roughly constant. And thus, something is keeping the nucleons from crowding too closely together. This point has been exhibited in high energy PP scattering involving 500 mega electron volt energy. And you can see here, actually these are the triplet S wave, singlet S wave and P wave scattering. You know what is S wave, P wave, etc. L is equal to 0 state is known as S wave, and L is equal to 1 state is the P wave. And for the S wave, this P and P can have either parallel or anti-parallel. That means the net spin may be either 1 or 0, and a 0 spin is the singlet state, and and a one state means it is the triplet state. So in this x-axis, we have the energy, and energy is increasing up to 500 MeV, and this is the phase shift. This we have already mentioned, and a positive phase shift always shows an attractive force, and the negative phase shift corresponds to repulsive force. So you can see that for both these triplet and singlet states, as the energy increases, the phase shift decreases. So if this phase shift is a measure of attraction, you can see that the phase shift decreases, which means that the attractive force decreases as the energy increases, or the as energy increases, you can say that the uh, protons may coming closer. So you can see that after this 300 MeV, the phase shift becomes negative, which means that after this 300 MeV, you are getting a repulsive force in the scattering experiments. So this is a proof for your repulsive core. And to account for the repulsive core, we must modify the potential we use in our calculations. For example, again we are choosing the square well potential, and before we have these two, we just consider these two now. We will write as VR is minus V0 when R less than capital R, where this capital R you are calling as the range of nuclear force, and it is equal to 0 when small r greater than capital R. This two we have considered. And now you are writing as VR equal to plus infinity, and always a positive potential shows a repulsive force, and if its value is infinity, which means that it is an infinite repulsive force or a very strong repulsive force. And VR will be plus infinity when your value of small r is less than r core, and this r core you are writing as a measure of the repulsive core. And these two are already known to us, and VR will be equal to minus V0 when your smaller r is in between your r core and capital R, our range, and it is equal to 0 when small r is greater than capital R, that is our range of nuclear force. And we can adjust R core until we get satisfactory agreement with the observed S wave phase shift. That means here, and the value R core equal to 0.5 femtometer gives agreement with the observed phase shift. So you can say that when the distance between the nucleons is less than this 0.5 femtometer or 0.5 Fermi or 0.5 into 10 raised to minus 15 meter, the attractive force becomes repulsive. And nuclear force have very short range. The absence of excited states in neutron is a consequence of the short range nature of nuclear force. We have mentioned that the range of nuclear force is 2 Fermi or 2 to 3 Fermi. And when the separation between the nucleons is greater than this value, nuclear force is not so strong. That is why you are saying that your neutron is a weakly bound system where the average distance that you have written as the neutron radius, which is nearly 4 Fermi. And you can see that uh, for most of the molecules that we have normally studying in atomic physics, or for most of bound systems, when you are going to an excited energy state, normally the separation between the particles in the system increases. This is a normal way. So your neutron is already a weakly bound system. And when you are going to an excited stage of neutron, the separation between proton and neutron increases further. That means that range will be much greater, or that range may be much greater than, or that distance between them will be much greater than the nuclear force. That means they can't be bind together at that distance due to nuclear force error. So that is an explanation for this. And the interaction between two nucleons consists to lowest order of an attractive central potential. That means the potential can be either V square, etc. So the lowest order, that means V, we are taking. The common character, that is the meaning of this lowest order. The common characteristic of this potential is that it depends only on the internucleon distance r. We therefore represent this central term as VCR. This C stands for the central. It's a central force. That means the force depends only on the distance and not on the any directions. The experimental program to study VCR would be to measure the energy dependence of nucleon-nucleon parameters such as scattering phase shifts, and then to try to choose the form of VCR that best reproduces these parameters. So we are saying that the potential depends as just VC R, or the lowest order, and not on the square or cube etc. of the potentials. And next property is the nucleon-nucleon force is charge symmetric. This means that the proton-proton interaction is identical to the neutron-neutron interaction. And before we saying this, we have to correct for the Coulomb force in proton-proton system. Because in proton-proton interaction, there is an attractive force due to nuclear force, and also there is a repulsive force due to the Coulomb force. So if you are correcting for that Coulomb repulsion, the neutron-neutron interaction and the proton-proton interaction are identical. So now you look this sentence. Here, charge refers to the character of the nucleon. That means proton or neutron, and not to electric charge. So this charge means, here we are mentioning that it is of the same type. That means you have same type as neutron-neutron or proton-proton. Here we are not mentioning about proton-neutron, NP, just NN and PP. So between NN and between PP, the force is same. That means of the same type, the force is same. That means the force is symmetric. That we are mentioned here. And evidence in support of this assertion comes from the equality of the PP and the NN scattering lengths and effective ranges. And of course, the scattering lengths and effective ranges are a measure of the force. Of course, the PP parameters must first be corrected for the Coulomb interaction. And when this is done, the resulting singlet PP parameters are in very good agreement with the measured NN parameters, which strongly supports the notion of charge symmetry. And this about, that means the same type of nucleons, we have the same force. And in a more general manner, you can say that the nucleon-nucleon force is charge independent. This means that in analogous spin states, the three nuclear forces Nn, Pp and Pn are identical. Here also, after correcting for the Pp Coulomb force. Charge independence is thus a stronger requirement than charge symmetry. So last one was charge symmetry. That means for same type, the force is same. But the more general term is charge independent. So this should be a more general property. Here the evidence is not so conclusive. That means in some books or in our textbook you can see that the nucleon-nucleon force is nearly charge independent. That is the meaning of this sentence. The singlet NP scattering length seems to differ substantially from the PP and the NN scattering lengths. However, we usually see that large negative scattering lengths are extraordinarily sensitive to the nuclear wave function near small r equal to capital R. Capital R is our nuclear range. And a very small change in psi can give a large change in the scattering length. Thus, the large difference between the scattering lengths may correspond to a very small difference of the order of 1% between the potentials, which can be easily explained by the exchange model. That means the wave function in NP and in say PP or NN are somewhat different, and this difference can be a reason for this difference in scattering length, and that difference in wave function can be explained based on our exchange force model. That is our next topic. So a small variation, only 1% variation in wave function. So this small variation can even cause a large difference, that you can see here. And this is, here you can see two wave functions which are very, very close. So for this one, you can see this arrow mark, and it is meeting the point small r is equal to capital R here. And when you are extrapolating, you are getting the scattering length as minus 17 femtometer. And when it is slightly different at a just different point, that point goes to minus 23 femtometer. So a large difference. So here you can see that only a very small change in nuclear wave function near small r is equal to capital R can lead to substantial differences in scattering length when the extrapolation is made. So actually this is the general sentence, but there is a small difference you can see, and that difference you can correct by the using this concept of exchange model. And the nucleon-nucleon interaction is strongly spin dependent. This idea we have already done, or we have already got this idea on our scattering experiments. This observation follows from the failure to observe a singlet bound state of the deuteron and also from the measured differences between the singlet and triplet cross sections. This we have done. The singlet and triplet cross sections are different. An additional term thus that must be added to the potential to account for this effect. So we have a potential here, and that potential is changing in accordance to the relative spins of the scattering particles. Obviously, the term must depend on the spins of the two nucleons, say S1 and S2, but not all possible combinations of S1 and S2 are permitted. The nuclear force must satisfy certain symmetries which restrict the possible forms that the potential could have. And the possibilities are, examples of these symmetries are parity, you are changing R to minus R, and time reversal, time to minus T. Experiments indicate that the internucleon potential is invariant with respect to these operations. That means they are invariant under parity and time reversal. Thus, terms such as S1 or S2, here you are using them as vectors, or a linear combination of AS1 plus BS2, A and B are some constants in the potential, would violate time reversal invariance and cannot be part of the nuclear potential. Terms such as S1 square, S2 square, or S1 dot S2 are invariant with respect to time reversal and are therefore allowed. And also, these terms are invariant with respect to parity. So, we can use S1 square, S2 square, or S1 dot S2. S1 and S2 are vectors. The simplest term involving both nucleon spins is S1 dot S2. To consider the value of S1 dot S2 for singlet and triplet states, we evaluate the total spin S as S1 plus S2. Vector S is vector S1 plus vector S2. And you can write this vector S square as S dot S, and this S can be written as S1 plus S2. So it is S dot S is S1 plus S2 dot S1 plus S2. And on multiplication, you will be getting it as S1 square dot plus S2 square plus 2 S1 dot S2. And from this expression, you can calculate S1 plus S1 dot S2 as S square minus S1 square minus S2 square whole divided by 2. That is why you are writing as S1 dot S2, an expression for this S1 dot S2 from the total spin as half S square minus S1 square minus S2 square. To evaluate this expression, we must remember that in quantum mechanics, all the squared angular momenta evaluate as. So, generally you are writing as angular momentum as, say if L is the angular momentum, in quantum mechanically, that L will be equal to root of L into L plus 1 h cross. That vector quantity you are saying. The similar way, S square will be h cross square. So, here it is a square value. So, it is h cross square S into S plus 1. So, S1 dot S2 now you can. The value now you are writing as the expectation value. That is the quantum mechanics. In place of S square, you have S into S plus 1. S1 square as S1 into S1 plus 1. S2 as S2 into S2 plus 1. Half is there, almost. S cross square is common. With the nucleon spins S1 and S2 of half, the value of S1 dot S2 for the triplet state is, for the triplet state, S is equal to 1. So, capital S you can substitute as 1, small s1, so S1 and S2 as half. And by solving this, you will be getting it as 1 by 4 h cross square. And for the singlet state, These are 0 and you are getting this as minus 3 by 4 H cross square. Thus, a spin dependent expression of the form S1 dot S2 VSR can be included in the potential and will have the effect of giving different calculated cross sections. So now we are introducing another potential VSR. Actually, we have now VCR. So a potential depends on the spin. The magnitude of Vs can be adjusted to give the correct difference between the singlet and a triplet cross sections, and the radial dependence can be adjusted to give the proper dependence of energy. We could also write the potential including Vc and Vs as Vc we have already mentioned. That is our potential depends on the central force and this is depends on spin. So you are writing it like this, where V1R and V3 are potentials that separately give the proper singlet and triplet behaviors. So this is just a mentioning of how we are changing now the potential. And the internucleon potential includes a non-central term known as a tensor potential. Evidence for the tensor force comes primarily from the observed quadrupole moment of the ground state of the tube. And a state, that means L is equal to 0, wave function is spherically symmetric. The electric quadrupole moment vanishes. Wave functions with mixed L values must result from non-central potentials. A mixed value means L is equal to 0 as well as L is equal to 1, L is equal to 2, etc. When you are getting such a mixture, it must be from a non-central potential. So, this tensor force must be of the form V of vector R instead of V of R. And for a central force, you are writing V potential as V of R. It depends only on the distance. That means for a spherical symmetry, to all directions, we have the same value. But this is vector R. For single nucleon, the choice of a certain direction in space is obviously arbitrary. Nucleons do not distinguish north from south or east from west. The only reference direction for a nucleon is its spin, and thus only terms of the form S dot R or S cross R, which relate R to the direction of S, can contribute. To satisfy the requirement of parity invariance, there must be an even number of factors, that is some parity concepts, R, and that means you are using that even number of R because, so if there is a negative parity in one, that means you have due to one term, you have an even term. So if you have an odd term, that means minus for a single term. If you have even number of parity terms, then that negative can be corrected to positive by multiplying with another negative. So this is a general consideration in parity. So to satisfy the requirement of parity invariance, there must be an even number of factors of R. And so for two nucleons, the potential must depend on the terms such as S dot R, S1 dot R into S2 dot R, or S1 cross R dot S2 cross R. And using vector identities, we can show that the second form can be written in terms of the first. That means this cross product can be written in terms of dot product with an additional term S1 dot S2, which we already included in VR, that we have already written in the spin dependence. So, thus without loss of generality, we can choose the tensor contribution to the internucleon potential to the form V T of R, a tensor dependence, into S1, S2, where VTR gives the force the proper radial dependence and the magnitude, and S1 2 equal to 3 times S1 dot R into S2 dot R divided by R square minus S1 dot S2. So this will give you this equation S1 dot R, S1 cross R dot S2 cross R, which gives the force its proper tensor character and also averages to 0 over all angles. And one more term, the nucleon-nucleon interaction may also depend on the relative velocity or momentum of the nucleons. Actually, forces depending on velocity or momentum cannot be represented by the scalar potential. But we can include these forces in a reasonable manner by introducing terms linear in P. P means our momentum or quadratic in P, and so on, with each term including a characteristic V of R. Under parity operation, that means when you are changing this P to minus P, and also under time reversal P to minus P, any term simply linear in P is unacceptable because it violates both the parity and time reversal invariance. So, single P you can't use. So, terms of the form R dot P or R cross P are invariant with respect to parity. This is an important concept. R dot P or R cross P. But still they violate a time reversal. So, a possible structure for this term is that is first order in P and invariant with respect to both the parity and a time reversal is V of R, R cross P dot S. When you are combining all these R cross P and S, it is invariant under parity and a time reversal. Here S, as you know, it is S1 plus S2. The relative angular momentum of the nucleons is, you are writing as L is equal to R cross P, and therefore this term known as the spin orbit term, this a normal term you are using as the spin orbit term in analogy with atomic physics, and now you can write it as V of SO, that means spin orbit R L dot S. Now here we have written a subscript, and this R cross P you are written as L. Although higher order terms may be present, this is only the first order term in P that satisfy the symmetries of both parity and time reversal. And the experimental evidence in support of the spin orbit interaction, we will discuss it from the observation that scattered nucleons can have their spins aligned or polarized in certain directions. Here you can see incident nucleons. So they can be either upspin or downspin. That means a combination. And you have a target nucleon. So you can see that this is upward spin. So particles in upspin are scatter to this direction and down spin to this direction. And when the target nucleon is with down spin, there also you are seeing that the up spin particles are scattered to this direction and down spin to this direction. And now we can explain this. So first you must get an idea regarding what we have mentioned in this figure. Consider the scattering experiment shown in figure A, in which an unpolarized beam, that means a mixture of spin up and spin down nucleons, is incident on a spin up target nucleon. Let us suppose the nucleon-nucleon interaction causes the incident spin up nucleons to be scattered to the left at angle theta, and the incident spin down nucleons to the scattered to the right at angle minus theta. Part B of the figure shows the same experiment viewed from below or else rotated 180 degree about the direction of the incident beam. We can also intercept or interpret figure B as the scattering of an unpolarized beam from a spin down target nucleon, and once again the spin up incident nucleon scattered to the left and the spin down nucleon scattered to the right. So here what we are mentioning is, this is the first one. You are observing incident nucleons and you are observing. You just observe, just say that you are observing it from here. That means this is a plane and you are above that plane. You are observing it. And in the second one, you are going to the down direction. Now, if you are standing like here you are coming to this side and you are standing to this side. So there also this is now under your leg. So when you are observing this from a surface, it is an upspin, and at this surface when you are going to this side and you are observing, it will be to the downside. So, but there is no change for these type of scattering, and that we will explain in the next slide. The results will be the same even in an unpolarized target, which could contain a mixture of spin up and spin down nucleons. When an unpolarized beam is scattered from an unpolarized target, the spin up scattered nucleons appear preferentially at theta and the spin down scattered nucleons at minus theta. So, even without particles with the spin or direction, you are now let us suppose spin orbit interaction can give rise to this type of scattering with the polarization. Figure shows two nucleons with the spin up incident on a spin up target. So that S is equal to 1. So here you have two incident nucleons, 1 and 2. So this is coming to this side, this is from this side. So here what you can observe is this incident photon is going like this. That means if this incident nucleus is attracted, it will go to this side. So you can say that it is repulsed and it is going like this. And the second one, it is attracted by this target and it is going to this side. So you can see that both of these are spin up. So this is spin up, this is also spin up. So total is spin 1. So to this side is moving to this side, and also so always that spin up are moving to the same side. Scattering that includes only S waves must be spherically symmetric, and therefore there can be no polarizations. The P wave, L is equal to 1 scattering of identical nucleons, has an anti-symmetric spatial wave function and therefore a symmetric spin wave function. These are only some quantum mechanical explanations here. But let us assume that VSO, that means spin orbit of R, is negative. That is the first assumption we are making. And we have to explain how these two are scattering like this. So, in a general manner, if it is attractive, both should come to this side. And if it is repulsive, both should, one should go like here and other should go like here. But we are saying that all the spin up are moving to one side. And how it is happening, that we have to explain. For incident nucleon 1, L is equal to R cross P is down into the page. How you can say that it is L? So for that you just see this figure. This is your X, Y, Z. So if you are considering X cross Y, the direction will be to this side. That means your X, and if your X and P are in this plane, X cross P will be towards you. X and Y are in this plane. X cross P, Y will be towards you. When you are rotating from X to Y, that means when you know that result, you have to, the rotation from one vector to the other must be anti-clockwise. So here, L, the direction of L you are saying. So L is R cross P, that is known to you. So you just move this to this point. So here you have L and you have P here. And R cross P means it is an anti-clockwise rotation. So if you are rotating from this side to this side, the resultant, the cross product direction will be towards you. And for this anti-clockwise rotation, it is inside to the screen. So here, this is R here, P here. So R cross P means clockwise. That means it is into the page or into the screen. And here, you can move this P to here. P, R cross P, anti-clockwise rotation. So it is clearly to this side. So one value you can take as minus and other as plus. So this value you are considering as minus L and towards you as plus L. That is a general custom. Therefore, L dot S is negative in this case, incident nucleon 1 case, because L and S point in opposite directions. So L dot S will give you a negative value. So the combination VSO of R, L dot S, VSO of R is always negative. Negative to negative is a positive. And so there is a repulsive force between the target and the incident nucleon 1, which is pushed to the left. That is here. This is the force, that means VSO into that L dot S is positive, so it is repelling. For nucleon 2, L points up, that we have already done. So L dot S is positive and the interaction is attractive because L dot S is positive, VSO is negative. So the attraction is, the resultant potential is a negative quantity, that means force or attraction, interaction is attractive. So incident nucleon 2 is pulled toward the target and also appears on the left side. So Spin up incident nucleons are therefore preferentially scattered to the left. By a similar argument, you can see that spin down nucleons scattered to the right. Thus, the spin orbit force can produce polarized scattered beams when unpolarized particles are incident on a target. That means unpolarized means for that particles there is no preferred direction. So after scattering, they are polarized, which means that the particles with different spin directions are moving to different directions. So in a particular direction, only particles with the spin in a single direction is possible. So that is why you can say that unpolarized particles can produce a polarized scattered beam. And this is one of the main reason to say that your nuclear force depends on the relative momentum. So now we have cleared that. In addition to that V of R, in general you can write as a combination of VCR. That is the simplest form. Then VSR should be there. Also VT tensor should be there. And also VSO means spin orbit coupling. So in your textbook, you can see a combination of all these potentials. So you can also refer your textbook, and that's all in this class. Thank you.